All right, so I'm going to show you how to make a quick Excel calculator for calculating standard error of the mean. Before we get to that, I'm going to really quickly go back through what the standard error of the mean is and why it's important. If you just need to go to the calculator, check the description below this video and you're going to find a timestamp. Just click on that. It'll take you right to where you need to go to make the calculator. But if it's your first time watching, this should help you with actually understanding what standard error of the mean is. So the standard deviation, if you remember standard deviation, describes the expected variance of a single score from the mean. So we have one score, and we can see how much variance we expect to see in that random score that we just pull from a group of scores. Most scores are going to be within one standard deviation. About 68% of them are going to be within one standard deviation. About 95% are going to be within two. And then slightly over 99% are within three. So that's just for a single score. But what about a mean, a sample mean? So the standard error of the mean describes the expected variance for a sample mean from the population mean. So this picture that I have here, which is terrible, like it looks like I traced a piece of spaghetti, and I might as well have, I mean, it's bad. But anyway, it's roughly a normal distribution. This is our population. But and our population has a mean of 100 and a standard deviation of 15. And what we're going to do is we're going to draw a sample. We want to see if the sample that we're getting, looks like this population. So we're going to take this sample and assume that we are grabbing a sample of people from this population. Then central tendency is going to tell us that the values are going to start to converge on the mean. Any single score, of course, is going to be anywhere around this distribution, just like it is, described by the standard deviation. Most of them will be within one. Even more of them will be within two standard deviations, and almost all of them will be within three, though some will be even further away than that. But because of central tendency, the mean of those scores that we start pulling for our sample are going to start converging on the population mean. They probably won't exactly be the population mean, but they'll start converging on it. The more observations we have, the closer to the population mean we're going to get. So take a look, and I'll show you what I mean. So these values are actual random values I pulled from a distribution with a mean of 100 and with a standard deviation of 15. So we have 115. This is exactly one standard deviation out. And so with one observation, the mean, which is described by this red arrow, is 115. So that's pretty far away from the mean, the population mean of 100. The second observation is 104. Well, now the mean is 109.5. So we're still above the mean a little bit, but we've moved it closer to the mean. So instead of being a full standard deviation away, now we're just a little over half of a standard deviation away. Then we have a point that is 97. So we take the average of those. Our new mean is 105.3. So now our mean is about a third of a standard deviation away from the population mean. And then we have a 71 come in, which is, almost two full standard deviations away. It's like one unit less than two standard deviations away. And the new mean is 97. And now we're only 3 units, whatever this measurement is, away from the actual population mean, because our new mean is 97. So you can see that more data points, even though they can be kind of far away sometimes, like we have one that's 1 standard deviation away, one that's almost 2 standard deviations away, but we do have 2 that are really close to the mean. And this is what we would expect with a normally distributed set of data. the mean is going to inch incrementally closer to the population mean, but it won't quite ever be the population mean. So clearly the expected variance is going to shrink with these additional data points. If we had, instead of 4 data points, if we had 10, we'd be a lot closer to 100. We can't just use standard deviation because we're shrinking the variance, the expected variance, with every data point that we add. We need to have a measurement that is sensitive to the number of data points that we're using, and that's the standard error of the mean. So what you've got here, standard error, this is the mean. Then you've got standard deviation here, and the number of samples on the bottom. It's actually the square root of the number of samples, but essentially what this is doing is it's taking your standard deviation and shrinking it by a factor of the number of observations you're using. So it's exactly doing what we said we need to do. We can't just use a standard deviation to look at how a population mean is, or how a sample mean is fitting a population mean. We need to shrink that variance as a function of the number of data points we're using. And this does that. This does exactly that. So let's now jump to Excel. We're going to build this calculator. One thing I'm going to show you before we start building the calculator is just to prove to you again how we incrementally inch closer to the population mean with more observations. So what I'm going to do is I'm going to build in here a mean and a standard deviation. Let's just use 115 again. And I'm going to generate some random values. And you can do this if you want. You can follow along. This is not something you'll be tested on. It's probably not something you'll ever use. It's not something you'll be tested on in the class ever. This is way beyond just biostatistics. It's probably not something you'll ever be tested on or ever use, like I said. But it's fun. Maybe if you teach statistics, you'll end up using it. So what we're going to do is we're going to generate a bunch of random values. And the way that we can do that with a normal distribution is if we say equals. Remember, everything starts with an equal sign. Everything in Excel, if you're doing any sort of formula, starts with an equal sign. And we're going to go norm.inv and then open parenthesis, because again, anytime you're using any of these predefined formulas in Excel, you have to put an open parenthesis after them, and then you have to close the parenthesis once you're done. And you can nest these kinds of things, which we will do, and you can create some really interesting formulas by nesting different commands. So we've got norm.inv, and what it wants us to give it is the probability. So this is going to be, the probability of any specific point on your normal distribution, like where you're pulling from the area under the curve. So you're going to need to give it some sort of random value. Then it's going to want to know the mean and standard deviation of your sample, or population rather, sorry. So to give it a probability value, we're going to type in RAND, and this is how you generate completely random values. RAND generates a random value between 0 and 1. And it just so happens that norm.inv is using a value between 0 and 1 as the area under the curve. So it's moving from the left to the right on the curve, and if you have a value of 0.5, that means that it's perfectly on the mean, and so it's at 50%. 50% of the distribution is to the left of that value, 50% is to the right, and so then the value that this command is going to return is 100. And if you have something that is, let's say, 68.68, then it's going to give you everything to the left is 68% of the distribution, and it just so happens that, well, I'm oversimplifying too much, but it's roughly around 1 standard deviation. It's actually going to be more than 1 standard deviation, because you're not just covering within 1 standard deviation, you're also covering all of the standard deviations to the left, and then the 2 standard deviations around the mean. So it's going to be more than 68%. It's going to be more than just 1 standard deviation, but it'd be around 120 or something like that is the value that it's going to give back to you. Anyway, so we're going to use this random value, and then we're going to plug in the mean. Well, what we're going to do is type in A2, but it's going to get more difficult than just A2. And then for the standard deviation, we want B2. Now, you might think that we're done, but no, we're not. Because what we're going to do is we're going to take this value that we get, go ahead and hit enter. So here's one value, but we want a lot of random values. And so we could pull down on this. So if you go click on the value that you want, you come over here to this little green dot in the bottom right corner of the cell, and your cursor changes. Notice that it goes from a fat white cursor to a skinny black cursor. If you pull it down, this is going to copy your formula downwards, but we have a problem. And the problem is, if you look at this formula, it's trying now to use A3, and the next one down is trying to use A4. So we have to tell Excel not to change the number that we're using here. And the way that you do that is with a $sign. So instead of just A2, we're going to say $2. Now it's locked in place. If we do the same trick again, click on that value and go down to this little fill handle. This is called the fill handle right here. When your cursor changes, you're on the fill handle. So then go ahead and pull down quite a ways. Let's do 50 observations. Now we actually get all the observations we need. If you click on any one of these, you can see that the formula is the same. We've got $2, so it hasn't tried to update the 2 and drag it down across the formula. Okay. So here's a bunch of random values, normally distributed random values with a mean of 100 and a standard deviation of 15. So here's what we're going to do. I want to look at the average of just 5. Let's just look at 5 of them. So here's 1, 2, 3, 4, 5. It's 105. Well, now let's do the next 5. So we had 1, 2, 3, 4, 5. Now we're going to do 1, 2, 3, 4, 5. 103. Oh, these are updating constantly, so it's kind of a pain. But anyway, let me just do a couple of these to show you what I'm trying to get at here. So 1, 2, 3, 4. Okay, so there's a whole bunch that have an average of 5. What we're going to do here is an average of 10 values. And the last thing we're going to do here is an average average of 20 values. Okay. Oh, well, why don't we also just do the average of all 50? Okay. So what you can see is these are all the same random values that we've got here. They update every time, but now that they've updated, these averages are from the same group. So you can see that here with just 5 values, we're off by 10 from the mean. Here we're off by 10. We're off by 7 here, and here we're off by about 5.5. And when you go to 10, we're doing an average of 10, then we're really close to the mean here. We're only off by 5. Here we're off by 6, and here we're off by 3.5. You go to an average of 20, we're off by 3.5, and we're off by 5.5. When you average all 50, we're off by 1. So you can see that when we're only looking at an average of 5, it's not uncommon that we're off by 10 or 7, fairly large values that we're off from the mean. And the more data points that we're actually putting together to average, the closer we're getting to the actual mean of 100. With 50 observations, getting an average at 101.4, it's pretty close. We can say that those are two groups that are very close together. There's no, statistical significance between those, most likely. Okay, so now that I've sufficiently bored you with that, let's do this calculator. Let's make this calculator for standard error of the mean. Looks like my Excel temporarily froze. I'm going to clear everything that I have here. There we go. And now we're going to do standard error of the mean. So we've got the standard deviation over the square root of n. So there's really only two things that we're going to need to put into this calculator. We're going to need a place for us to input standard deviation. We're going to need a place for us to input the number of samples. And then we're going to need to calculate the output, which is the standard error of the mean. So here's standard deviation, here's n, and let's just say it's 15. And let's say we did 50 observations, just like we just did. And then here I'm going to put in SEM. And this is right here where we're going to build the actual calculator. So I like to mark the user input values with green. I'm building it, but I'm the user, whatever. It just makes it easier for me when I come to use it. That green is what I'm putting in, and yellow or orange or something like that is what I'm getting out. So, that was text. I don't want to change the color of the text. What a weirdo. Okay, there we go. So the output value is going to be in yellow. It's like, hey, look here. Green is like, go ahead and change this. Yellow is like, hey, look at this. All right. So our formula is standard deviation divided by the square root of n. What is the first thing that we have to do when we're building any formula in Excel? It is an equal sign. So you start with an equal sign. Okay, the next thing that we want is the standard deviation. So you can use your arrow keys and jump over to standard deviation, or you could click right here on A2, or you could just type in A2. It doesn't matter. We're going to do A2 divided by And we need the square root of n. Square root is a command that we can use from Excel. The command for square root is sqrt. It looks like squirt, but it means square root. And since you're using an Excel command, of course you have to have an open parenthesis. So we're going to do sqrt open parenthesis, and that means square root of, and then you put in what you're taking the square root of. So here we want to put in the square root of n. So again, you can use your arrow keys to jump over to B2. You could physically type in B2, or you could click on B2, whatever. It all gets to the same B2 in the formula. We're going to close our parentheses and hit enter. And there we go. A2 divided by the square root of B2, or standard deviation divided by the square root of n. Gives us, with standard deviation of 15 and an n of 50, the standard error of the mean is 2.12. So you would expect that with 50 observations, your new mean would be off by about 2 units each time. Remember, the one that we just looked at was off by 1.5, something like that. So it's totally within this, absolutely within this. And there you go. So you can change things right here. If you save this as it is, now you've got a calculator that's going to let you update the standard error of the mean as you wish. You can change the standard deviation to 30 or 40, I guess, since I accidentally typed 40. So a larger standard deviation is going to lead to a larger standard error of the mean. You can see that even with 50 subjects, now our standard error of the mean is 5.6 instead of 2. What happens if you get more subjects? If you get 1,000 subjects? Well, now your standard error is 1.3. What if you only had 30? Now it's 7.3. So you can save this, change these two values, and end up with the standard error of the mean that you need. Just because I like to do things completely, I'm going to go ahead and put a thick outside border around all this. Since it's all together, it's one little formula package, and there we go. Okay, so why are we talking about standard error of the mean? Well, it's in so many of these formulas. Look at the bottom of this z-score formula. There it is. T-score formula. There it is. Right here in the confidence interval formula, there's standard error of the mean again. And it's also kind of the mean square in an ANOVA, but in a different form. It's kind of the same thing. It's just masquerading as a different number. There it is. So it shows up over and over and over again. Now, even once you're done with the class and you think there's no reason why you need to compute standard error of the mean, because now we've showed you how to do a t-test with a couple commands, or do a z-test with a couple of commands, or you have this calculator that gives you standard error of the mean. Why do you need to know it after you've passed this? Well, it just so happens that error bars, which are these things on the graph that I'm pointing to with these dots, with these arrows, tend to be either a 95% confidence interval or 2 standard deviations. 2 standard errors. So it's either a 95% confidence interval or 2 standard errors that you're showing. So you're still going to have to use this dumb formula every time you make a graph if you want to represent your error bars the way that most people do. And if your knowledge of statistics is really good, you'll see that a 95% confidence interval error bar or 2 standard errors are pretty much the same thing. I know some of you are shaking your heads. Yeah, I see how that's exactly the same thing. 2 standard errors versus 95% confidence interval. What's really the difference there? Some of you might not know. If you don't know, try to figure it out. If you do know, good job. You're going to do really well on the exam. your knowledge of statistics is good. If you don't know, check it out. The answer is in the description. I'll tell you why. They're pretty much the same thing. All right, that's it for the standard error of the mean calculator. This is used in the calculator for z-test, t-test, and confidence interval. And those are all going to be linked probably on the screen right now. You've got a link to some of them, and the rest of them are down below. Okay, I'll see you later.